Hello. In this video, we're going to look at the slope of a tangent line, which is section 2.7 and 2.8 in your textbook. Now, the motivation for this section is, well, a tangent line. And you might have never seen a tangent line before. You might have from physics and from some other science courses, or you might have never seen one. Either way, we're going to go ahead and pull up a Desmos animation to help illustrate what a tangent line looks like. So here we have our red graph and our blue line. And we'd like our blue line to be tangent. Now, tangent means that it just glances off the graph. It's just briefly touching the graph. It's parallel to the graph at that point. So right now, it's clearly not tangent. And if we move this point over here, we can drag the line until it looks closer to tangent. This is still not looking great if we consider the point where we want it to be tangent over here around -4. It's not looking great for that tangent line, but we can keep going. We can keep moving that dot closer and closer. It's looking a little bit better, And so we can go closer and closer and closer, and that's looking like a pretty good tangent line. But if we put that point as close as we can right on top, if you notice, the line disappears. And that's because technically, to make a line, at least using the method I have on this Desmos animation, you need 2 points. Because that's what you learn about lines. 2 points make a straight line. And if we move this second point all the way to where that tangent point is, well then you don't have 2 points. You only have 1 point because both points are in the same place. And Desmos seems to break. It seems to fail at this point because it can't make a line with just 1 point. But hopefully you see the intuition here, this idea that, well, if instead of getting right on top of that point, instead of going exactly where that point is, so both points are identically on top of each other, what if I used some type of limit? What if I took this second point and I had it approach that first point? Well, the limit doesn't care what happens when the 2 points are exactly on top of each other. It's all about this idea of approaching, of getting closer and closer. And so it seems like this idea of a limit might save me from the breakdown of having both points exactly at the same place. Now, let's see if we can go ahead and work that through with actual algebra. So we need a few different concepts. First off, we're going to have to recall the idea of slope. So if you remember, slope is equal to, at its most basic, rise over run. Sometimes you might have written it with a little more complicated formula, y2 minus y1. Over x2 minus x1. So that's like saying we have our point here, maybe x1, y1, x2, y2. But what we're going to do is label these points a little bit differently to help our algebra work better. This point, I'm going to fix it at a f of a. And this point, I'm going to allow it to vary. So I'm going to call it x, f of x. In math, we tend to use letters like a, b, and c for constants, and letters like x, y, and z for variables. So by using a here, I'm indicating that this point is fixed at a particular point a, but I'm keeping it general. I'm not saying -4, -3. And this point here is x, which means I'm going to allow it to vary all along the graph. So the slope formula would then be the same thing, y2 minus y1 over x2 minus x1. But the x1 and the x2 are now x and a, and so on and so forth. So the slope would be equal to y2, which is f of x, y1, which is f of a, x2, which is x, and x1, which is a. Now, like we mentioned in the Desmos animation, we want this point to get really close here. In other words, we want the x value to approach a. So if we're going to use a limit, we could write this as the limit x approaches a, f of x minus f of a over x minus a. Now again, if you notice, when we go to plug this in, we're going to get f of a over f of a, which is 0, and a over a, which is 0. So we're going to have some more work to do. This is going to be a do more work limit, but hopefully there will be work that we can actually do, and hopefully we'll be able to get some type of tangent line here. So let's do a concrete example. Let's consider the function x cubed. So we want to find the slope of the tangent line. We'll find the particular point 2 and f of 2, or -3 f of -3, or maybe a f of a in general. So let's start with the first one. So here we have a equal to 2. So we write our limit. X is going to approach 2 of f of x minus f of 2 over x minus 2. I'm just rewriting the above limit, but putting in 2 for a. Now we can also put in for fx. We know f of x is going to be the function x cubed. So we're going to get the limit x approaches 2 of x cubed minus, well, f of 2 means we have to plug 2 into this. So 2 cubed is, well, I could write 2 cubed. That'll be 8. Of course, if we try to plug in this limit, you're going to get 8 minus 8 over 2 minus 2, so you have to do more work. But it looks like the work we can do is a difference of cubes. Hopefully you remember your difference of cubes formula. It's x minus 2, x squared plus 2x plus 4 over still x minus 2. Hey, it looks like we've got something to cancel. There's something in common, the x minus 2. So we're going to go ahead and cancel that out. And that's going to give me the limit x approaches 2 of x squared plus 2x plus 4, which we can simply plug in as, well, 2 squared plus 2 times 2 plus 4. So 4 plus 4 plus 4, which is 12. Now, you might not believe that this is indeed correct. What does this 12 represent? This should be the slope of the tangent line when x is 2. And let's go ahead and check on Desmos to see if this is true. So if we go ahead and graph y equals x cubed and y equals 12x, we have a bit of a problem because the 12x doesn't look tangent, and that's because the line is just 12x. It's right through the origin. We need to move that over to make sure it's in the right point. Now, I just kind of eyeballed this, and it looks like it's about minus 16. If we move that line down a little bit, it should be in the right place. So you can see here that the blue line, which is our tangent line, looks perfectly tangent to x cubed. And the point where it's tangent is at x equals to 2. Of course, you can see y is equal to 8 there as well. So it's at that point 2 and f of 2. So there's our line. It looks tangent. It looks like 12 is the correct value for the slope. If we would have tried some other value, like maybe 6 here, we would see, of course, you need a different value to move it up or down by. So this value wouldn't be 16 anymore. This might be 8 or maybe 6. We could try 4. There we go. So it's still going to go through the graph, but now clearly this does not look tangent over at 2. It's skewed. It's not the right slope. We need that value of 12 there to make it look nice and perfectly tangent to the graph. And we are able to come up with that value of 12 by using our limit. So let's go ahead and try part B with negative 3 and f of negative 3. So here for part B, we have a equal to negative 3. It's the same setup as before. So we do the limit as x approaches negative 3 of f of x minus f of negative 3 over x minus negative 3. Again, we can write f of x as x cubed. So limit x approaches negative 3 of x cubed minus negative 3 cubed over, and we could simplify that to x plus 3. So a little bit of arithmetic on the top will give us x cubed plus 27. Now if you notice, this is a sum of cubes formula. So we can go ahead and factor as x plus 3, x squared minus 3x plus 9 over x plus 3. Again, the x plus 3 cancels. This is very similar to the previous example we had for part A. And we'll have the limit x approaches negative 3 of x squared minus 3x plus 9. We can plug that in to get 9. Negative 3 times negative 3 will be 9, so 9 plus 9 plus 9, which gives us 27. Again, you could check this one if you want on your own. You could plug in y equals 27, and you would have to adjust to find the right y-intercept. But this would indeed be the tangent line over at x equal to negative 3. Now, let's go ahead and try part C. So for part C, apparently, they want us to have just a. So a is equal to a. Just the letter a, no specific value. Well, we can try the same limit. We'll do limit x approaches, well, a of f of x minus f of a over x minus a. Seems a little bit weird to have just an a in there, to not have a number. But let's just continue on. We'd get x cubed minus f of a would be a cubed over x minus a. Here we're going to have a difference of cubes formula. And in fact, I think it's a little easier to factor because there's no number. So we just use the formula, which is x minus a, x squared plus ax plus a squared over x minus a. Of course, something cancels, the x minus a. So you have the limit x approaches a of x squared plus ax plus a squared. Now remember, when we do this, we're going to plug in for x. So this is going to become a squared. The a remains as it is, but this becomes a times a, which is another a squared. And the limit of a constant is, of course, the constant itself. So we're going to get a squared plus a squared, which is 3a squared. Now, hopefully you see a bit of connection here. Notice how we had 9 plus 9 plus 9. Here we've got a squared plus a squared plus a squared. Back in our original one over here, we might have wanted to clean this up a little bit. We had 4 plus 4 plus 4. Of course, notice 4 is 2 squared and 9 is negative 3 squared. Our final answers here are actually all contained in this general case. So let's just say that you were handed 3a squared. Would you be able to automatically do question A and B? Let's say we did question C first. If we knew that the answer was 3a squared, then for part A, we have a equal 2, and so our answer would be 3 times 2 squared, which would be 12. And for B, we have a equals negative 3. So our answer would be 3 times negative 3 squared, which would be 27. You can do part A and B now in just one line, because 3a squared is almost like a formula. It automatically gives you the answers to the other questions because you did it in general. And so doing it in general here is actually very, very useful, very important. It's a concept we'll look at in a little bit as we go through this video, because while you can do it for specific numbers like 2 and negative 3, if you do it for just a, you end up with the formula 3a squared, which is much more powerful because then you don't have to do it at a specific value. You do it at any value, and then any value you want just gets automatically plugged in. Now, if you remember on Desmos, we had to find that negative 16. I had to put that onto the equation, and that made it a little tricky to graph. That's because all we've done so far is come up with the slope of the tangent line. We also need to get the equation of the tangent line. So the equation of the tangent line is as follows. Let's let m be the slope of the tangent line that we've already found, and we're going to have it at a point a, f of a, to the curve y equals f of x. Of course, m comes from the limit x approaching a of f of x minus f of a over x minus a, and this limit must exist. Then this formula, y minus f of a equals m x minus a, is called the equation of the tangent line at the point a, f of a. Now, if you've never seen this formula before, I apologize. It is part of the grade 10 curriculum, but you might not have ever seen it before. Sometimes it just gets missed in the hustle and bustle of school. So this is called the point slope formula. The point slope formula sometimes would be written as y minus y1 equals mx minus x1. Now you're probably familiar with the y equals mx plus b. That's your classic formula for a line. it takes the slope and the y-intercept and creates a line. But there are other formulas for making lines, and this one in particular is quite useful. It's called the point-slope formula. So you take a point, x1, y1, and you take a slope, m, and you plug it into the point-slope formula, and it also gives you an equation of a line. In this case, our point x1, y1 is the value a and f of a. So let's go ahead and try it on our example. We had our function x cubed, and we wanted to find the tangent line at those three locations. So for a, if you remember, we had our point. Well, they tell us our point. The point is 2, and then f of 2, which is 8. And we have our slope, which we found was 12 from before. So we just plug it into the point-slope formula. Y minus 8 equals 12, x minus 2. And there we go. We can go ahead and check this on Desmos. So again, here we have our graph of y equal to x cubed. And we put the tangent line down, and you notice it just snaps into place just perfectly at that point 2 and 8. So again, we don't need to deal with that negative 16 or trying to find the y-intercept. We can just type in this equation, and we get a beautiful tangent line. Now, for those of you wondering where that negative 16 came from, this is just some extra. You could go ahead and convert this into the other form. So you'd have y minus 8. You could expand the 12 as 12x minus 24. You'd move that 8 to the other side, and you'd get, well, plus 8, which makes a 16. So you could convert this formula into the y equals mx plus b formula. You don't have to, but just in case you were wondering where the negative 16 comes from, now you can see it. So let's go ahead and do part B. So we had a point, which was at negative 3, negative 27. And we had a slope, which was m equal to 27. And so we just plug those into our formula. So y minus y1, so subtract 27, negative 27, is going to be 27x subtract negative 3. Now again, if you wanted to, just for extra, you could turn this into y plus 27 if you wanted, and you could turn this into x plus 3. But you don't have to. You're welcome to just leave it in this form here. Now let's try that third one. So for part C, remember our point's a little weird. It's at a and then f of a, which is a cubed. And the slope was just m equal to 3a squared. So our formula is y minus a cubed equals 3a squared x minus a. Now let's take a look at this one on Desmos. So the remarkable thing about this formula is because it's in general, Desmos knows that it could be any number you want. And so you can actually take that value, that tangent line, and you can slide it all along the graph. And at any point, it's going to be perfectly tangent. You're going to have a beautiful tangent line that you could actually animate. Now, the animation doesn't really come clear through on this video, but you could go ahead and have it play, and it would run through all of the different possible values of a. And it looks quite beautiful as this tangent line, it almost rides along the graph. It looks like a very cool animation as it goes through it and is continually tangent all the time. Now let's try a quick multiple choice question here. Given the equation of the tangent line for f of x is y minus 2 equals 4, x plus a, the slope of the tangent line is 2, 2 and 5, 2, negative 5, or 4. So go ahead and pause the video and give it a try. All right, the correct answer is 4 because we have it here in its proper format, y minus y1. So the point is actually 2, negative 5. That's our point. But the slope is coming from right here. So the slope is m equal to 4. So the answer would be 4. Now what we've been working with is the slope of the tangent line. And it's definitely useful, but we want to get a bit of a better formula, a better way to work with it. So what we're going to do is transform this limit as follows. Instead of having the limit x approaches a of f of x minus f of a over x minus a, I'm wanting to approach 0. Now the reason I want to approach 0 is 0 is a great number. When you plug in 0, lots of things cancel and disappear. 0 is a lot nicer of a number to have, and if you look, the bottom of this thing is actually approaching 0. As x approaches a, the bottom approaches 0. So it would be nice if we just had the 0 in there already. And apparently we can take this limit and make it look like this limit. Well, how do we do that? We simply let h equal to that bottom, x minus a. So if we do that substitution, then clearly this denominator will become h. And like I mentioned, as x approaches a, h will approach 0. Now f of a stays as f of a, but how does this f of a plus h come about? It used to be an f of x. Well, I simply take this formula that I've defined, and I go ahead and solve for x, which means I'd have to rearrange the a, so a plus h would be equal to x. And then that means my f of x, the x is going to become a plus h. So this is an equivalent formula for the slope of the tangent line. This still gives here slope of tangent line. But it's going to be a more useful formula because it's cleaner. H is going to 0 and we just have a single letter in the denominator. And this allows us to define probably the most important definition you're going to see in the course. We get to define the derivative. So you definitely want to star this in your notes, the derivative. The derivative of a function fx at a point x, f of x, is denoted by f apostrophe x, usually read as f prime x, and defined as f prime x equals, the limit as h approaches 0, of f of x plus h minus f of x over h. All we've done here is instead of writing a, we've written x. So we've just replaced the a with an x. And of course, this will always be true provided the limit exists. Sometimes limits don't exist, and so we need to add this statement that it's going to be provided the limit exists. So what we can say is that the slope of the tangent to fx at a f of a is the same as f prime of a. So it helps us have better notation. Instead of having to write the limit every time when we want to talk about the slope of the tangent line, we can talk about the derivative. We'll still need to use a limit to actually calculate it, but we can say f prime of a. This quantity here represents the slope of the tangent line because it's saying, well, we take a, we'd plug it in here, we'd do a limit, we'd get a slope of a tangent line, but it's more compact. So f prime a represents the slope of the tangent line. Now to calculate f prime x, we're going to use a nice series of steps that'll be the same every time. Step 1 is we're going to calculate f of x plus h. We're going to have to expand x plus h because that'll be part of the function. Then we're going to have to calculate f of x plus h minus f of x. That's going to be the numerator here. Then we're just going to divide by h and calculate the limit. So those 3 steps will make doing these slopes of tangents very routine for us. So let's try an example. We have f of x as 3x squared minus 7x plus 2. We want to find f prime x and state the interval where it exists. Again, remember, sometimes limits don't exist, which means sometimes derivatives don't exist, so we need to be careful about that. So let's go ahead and try step number 1. Step number 1 says we have to calculate f of x plus h, which means everywhere you see an x, it gets replaced with x plus h. This is technically function composition from pre-cal. Everywhere you see this x and this x, you replace it with x plus h. So this would give us, well, 3. We have to expand this as x squared plus 2xh plus h squared. Here we could expand this as negative 7x, negative 7h plus 2. Next up, we'll put that 3 into each of them, so 3x squared plus 6xh plus 3h squared minus 7x minus 7h plus 2. So a lot of different terms there, and it doesn't actually look like anything else simplifies, so we're just going to have to leave it there. Step 2, though, is going to allow some simplification to happen. It always does. So f of x plus h minus f of x. So we rewrite this first part, 3x squared plus 6xh plus 3h squared minus 7x minus 7h plus 2. And then we subtract off f of x, which is just our original function. So we're going to subtract 3x squared minus 7x plus 2, subtracting off our original function. Now if you notice, there's some terms that are the same. 3x squared, subtract 3x squared is gone. The 7x here is negative 7x. But the 7x here is going to be positive because the negative negative will make a positive. Now when I'm canceling a second term, I often use 2 slashes just to keep track of what I'm canceling. Finally, the plus 2 here is going to cancel with the negative 2 over here. I'll often use a backslash for another cancellation there. So let's see what we have after all that cancellation has been done. Well, we have 6xh, 3h squared, minus 7h. That's all we've got. It's actually a lot simpler. So let's move on to step number 3. For step number 3, we calculate the limit as h approaches 0 of f of x plus h minus fx over h. That will be equal to, well, we have the limit, h approaches 0, 6xh plus 3h squared minus 7h over h. Now if you were to plug in h equal to 0, you get 0 plus 0 plus 0, which is 0 over 0. So it's 0 over 0. We need to do more work. But I think we can see the work to be done. There's an h in common with all the terms on the top. So we'll get the limit h approaches 0. H, 6x plus 3h minus 7 over h. We can go ahead and cancel out that h, giving us the limit h approaches 0 of 6x plus 3h minus 7. And finally, we can plug in h as 0. Now we know that the x in this case is a little strange because the 7 is a constant, so that makes sense. The limit of that will just be a negative 7. The 3h is going to go to 0, but remember 6x, it's technically a constant with respect to h because there's no h involved here, so 6x just comes out straight as 6x. You don't plug in for the x because it's not an h. So you get 6x minus 7. And there's your answer. That is f prime x. Now if you look at it, you have to determine the interval, and you just basically ask yourself, when is this function defined? Does it have any denominators of 0, any weird square roots, anything like that? Well, no, it looks like a nice polynomial. It's defined everywhere. So we could add here that this is true on the interval negative infinity to infinity. Now before we move on to the next question, I want to pop this answer of f prime x up next to our original function. So we had fx, which was 3x squared minus 7x plus 2. In the end, we found the derivative, which was 6x minus 7. And the question I would ask you is there some kind of connection between these two? Do you see some kind of connection? Do you see some kind of pattern? I mean, I think it's pretty obvious, at least to me, that this negative 7 is somehow connected to this negative 7x. Surely you see the connection there, that this is somehow related to that. But where does the 6 come from? Is the 6 maybe like 3 times 2? What happened to that 2? What happened to the x squared? There's still some unanswered questions. But the idea that there might be some way to relate fx to f prime x, it feels like there's some kind of method, some kind of connection there. And in particular, this down here was a lot of work. Would there be a shortcut? Would there be a way of jumping from fx to f prime x in one step? I mean, I don't think we could do that right away, but does it feel like there might be some type of method? Maybe there is, maybe there isn't, but keep your eye out for it as we start to go through these derivative questions and see if there's a way to relate the formula for the function and the formula for the slope of the tangent. Is there a way to shortcut it? Now let's go ahead and do a multiple choice question here. Given that the derivative of fx is 6x minus 7, since we just calculated it, determine the slope of the tangent line at 1, negative 2. So go ahead and pause the video and give it a try. Alright, so remember this formula, the derivative, is the formula for the slope of the tangent line. So if you need to find the slope of the tangent line, you take this point, and in particular, you take the fact that x is equal to 1, and you calculate f prime of 1. So 6 times 1 minus 7, which will be negative 1. So the answer will be C, negative 1. So for homework, you can go ahead and try the definition of the derivative worksheet. Some of the questions get a little challenging near the end with the square roots and with the fractions, but you can definitely do the ones with the polynomials, the first 10 on there. And you can definitely give the ones with the square roots and with the fractions a try. The limits will be a little tricky, but I think you can work them out if you're persevering with them. And when you look on the back, as you see your answers, see if you can find connections between the function and its derivative. See if you can highlight any of those relationships as you work through it. So hopefully you enjoyed this video, and as always, thanks for watching.